give you one example, which is picked because it illustrates one of the many groundbreaking contributions by the third of this year's laureates, Anton Zeilinger. So to understand this, you have to know that a goal of quantum mechanics today is to build a quantum network. What is that? A quantum network is a series of nodes, and these nodes should be able to communicate via quantum entanglement. In these nodes, you can have quantum devices like encryption devices. How do you build such a network? It's difficult because entanglement is brittle. If you send it to an optical fiber, it very easily gets destroyed. So you need some new trick. And just an amplifier won't work because amplifiers destroy entanglement. So here is the trick, the method that Anton Zeilinger came up with. It's called entanglement swapping. You have two of these bell pairs like this. One of the particles here, one, and the other four goes far away from each other. The two other comes together. Here, you make a measurement, so you entangle particle 2 and 3. And then magically, 1 and 4 becomes entangled, although they had never been close to each other. It's wonderful. So now you can think of doing it in a chain. You do one, you could do another, you do a third, etc., and you can build up a network. Another method to get long-range entanglement is not to use optical fibers, but to send just light through the air. And I'll just give you one spectacular example of this. And that was in 2018. There was an intercontinental quantum link set up using the Chinese MICUS quantum satellite between the group of Jianwei Pan, the Academy of Science in China, and with Anton Zeilinger's group in Austria, over 7,600 kilometers, pretty amazing. And now we are at the forefront of current research, and I will just end with a few comments. So today we honor 3 physicists whose pioneering experiments showed us that the strange world of entanglement and bell pairs is not just the micro world of atoms, and certainly not the virtual world of science fiction or mysticism, but it's the real world that we all live in. And researchers now, all over the world, they use entanglement and bell pairs, both in curiosity-driven fundamental research and in utility-driven applications such as quantum cryptography or quantum computing. Thank you for listening.